Yes, class. Good evening. So in the last class, we had completed with resonance. Resonance was the condition where maximum current was given and minimum impedance was there. Z that was obtained, and its magnitude was equal to the magnitude of the current in the circuit. All right. Then we had done one of the series circuit that was left, LR circuit. After LCR circuit, LR circuit is left. So in case of LR circuit, you do not have capacitance component. So from LCR circuit, just remove the capacitor part. R is the resistance, L is the inductance. So here resistor will be there and voltage you will draw. Only these two components will come. So even in the formula for impedance, when you write the formula for impedance, instead of XL minus XC square and all those things that we obtain, we will be just getting XL square because XC component is not there, and tan phi will be XL by R. Otherwise, in LCR circuit, where all the three components were added, XL minus XC was included, or XC minus XL. Now only XL will be included. One numerical also we had completed. Series RC circuit. See, class, in case of series RC circuit, now remove inductor. What are you left with? Resistor and a capacitor. So in case of resistors, current and voltage are both in the same phase, while in case of a capacitor, current leads the voltage by 90 degrees. Whereas in inductor we had, see, you have to remember this part, which leads which quantity by what amount. Fine. If you do not remember this part, which leads, otherwise remembering this LCR circuit becomes difficult. Because if you've understood for those individual circuits, no, then understanding and remembering for these circuits becomes easier, because everything is based upon what leads by what. See, by just remembering the fact that current leads here and voltage lags, so you will draw the phasor diagram where voltage will be lagging behind the resistor. So this part will be done. This is the resistor. This will be the voltage of capacitor lagging by 90 degree. Voltage of resistor. Resistance will be R. Here resistance will be XC, right? And same thing, same derivation that we'll do. E square is equal to not E square, E naught square. Same thing, same derivation we'll do for it. So E naught square will be equal to VR square plus VC square. Now you will not be having VL square this time because this is RC circuit. Now put in the value of IR, you will get I common, same steps, exactly same steps you will get. It's just that where you were getting XL square, now you have XC square. So tan phi will also be XC by R. This is just RC circuit that was left in the last class when we were discussing. So quickly note this down. This RC circuit exactly similar to XL. Wherever you had XL, now you have XC. Wherever you had inductance, now you have capacitance. So note it down. If you're still not able to understand any part, let me know. I'll repeat that part. Just note it down, then we'll start with powers. Powers in an AC circuit. Yes, this is a derivation, a very small derivation similar to the derivation that we have done. This is a derivation for the impedance of this. See, so this was about all the circuits that were present. So how many circuits we have done? 3 individual circuits, C class. Those 3 individual circuits we have done, which included first your purely resistive circuit, then it included purely inductive circuit and purely capacitive circuit. So these 3 circuits, then plus one circuit that was LCR circuit, where it included all these 3. And right now 2 circuits we have covered. One in the last class we had covered LR circuit, and right now we have covered RC circuits. So all these circuits are there. Whenever if you get time on a spare sheet or paper, then do one thing. Write down all these and write down the phase difference between. If you know the phase difference, then these are based exactly on them. Now, see, power and energy is one of the topics that is left, and transformers. So this is not a very huge topic. See, instantaneous power that is present. This is mainly, see, normal power is given by P is equal to VI. So instantaneous power, it becomes EI. And E is what? E is E naught sine omega t. And I is what? I naught sine omega t. This we have studied. So place it over here. Now see, there will be a certain phase difference if this is E naught sine omega t. So voltage and current, whenever you're calculating instant, fine. If you're calculating, but in AC circuit, voltage and current vary sinusoidally. It means you will add not to just omega t minus phi as well. This can be written for E naught also. This can be written for I naught also, depending upon whatever is the case, whether whichever is leading. So I am taking randomly right now. Answer will be same from both of it. Because see, why answer will be same? Even if you write E naught sine omega t multiplied by I naught sine omega t minus phi. Even if this was for here, minus phi was for here, you would have written sine omega t minus phi. Since it is in multiplication, A into B or B into A will give you the same answers. That's why there is no difference. According to the situation you can take. And if the derivation comes, you can easily write, take E is equal to this, E naught is equal to this, like this. Now see, okay, if this is power, let's rearrange this. This becomes E naught, I naught, sine omega t, and this term, I'm just rearranging this. And this becomes sine omega t minus phi. All right, this is power. Now we have to simplify this. See, sine theta into sine theta. If you have this identity, you will get E naught, I naught, by 2. I'm just multiplying 2 above and below because I want to use one identity. So what I'm doing, I'm multiplying 2 above and below. So here 2, and in the numerator also I'll get 2. Now see, why am I doing this? Because this identity will be now valid. The identity is whenever you have 2 sine A, sine B. This was A omega t and B is omega t minus phi. So this is written as cos A minus B. All the students who already have mathematics, they must be knowing this identity, minus cos A plus B. And those who do not have maths, you can just make a bracket and write down on a sheet, in the corner of a sheet or even within the derivation. So we'll substitute this identity on here. In this, we will substitute it. So this becomes, see, cos phi it will become, because cos A minus B. So omega t minus phi. It means only phi will be left from here. And you have minus cos omega t will get added minus phi. A plus B means omega t plus omega t. See, this was omega t minus plus phi. This got cancelled. I was left with phi. This is plus, so omega t plus omega t minus phi. It means this minus phi, this gives omega t minus phi. That's why I'm having minus phi to phi. Just substituting it in the identity. All right. Now see, if you take the average, whenever you take the average of cos to omega t minus phi, this is what? This is the second cosine term. We call this as the second cosine term. Second cosine term is cos theta is the first cosine term. Cos 2 theta becomes the second cosine term. Just a second. So this is the second cosine term. So whenever you take the average of second cosine term, average of this is 0. It means this entire term has been deleted for us. Within this bracket, this part will be 0 because this is second cosine term. So what are you left with? You are simply left with power is equal to E naught I naught by 2 cos phi, right? And even if you wish, you can see. Can anybody tell me what is root 2 multiplied by root 2? What is root 2 multiplied by root 2? What is the value that we obtain? Yes, Fahad, right. It's 2. So it means I can write this 2 as root 2 into root 2. No difference. Can anybody tell me what is E naught by root 2? Yes, class, E naught by root 2. E naught by root 2, I naught by root 2. Yes, who has answered? Sahar. Perfect. ERMS and IRMS. This is ERMS, this is IRMS. So you can write the formula of power. Power is written as ERMS IRMS cos phi, where phi is the phase difference. Now see, if you have a purely resistive circuit, so we have seen for purely resistive circuit, current and voltage are in the same phase. So it means if voltage and current are in the same phase, phi will be 0. So this becomes what? P is equal to IRMS, ERMS, cos 0 degree. That gives you IRMS multiplied by ERMS. And for purely capacitive or purely inductive circuits, we have seen current either leads by 90 degree or lags by 90 degree. So phase difference remains 90 degree. So P is equal to ERMS IRMS cos 90 degree. Directly this is 0. So see the difference. For purely resistive circuit, power is maximum. For purely capacitive or inductive circuit, power is minimum, least, it is 0. Now, before you copy this down, one small term that is present, which has been added right now into your syllabus this year. So a lot of chances are there that wattless current can be asked to you in the exam. See what is meant by wattless current. Definition is already written. The alternating current which is obtained when average power through AC circuit is 0. So in case of, okay, power factor we didn't do, no? See, when the power is 0, that the current that will be obtained at that time, that will be known as the wattless current. So average power, whenever the average power is 0, like for purely capacitive and inductive circuits, where P is 0. So now the type of current that will be present within the circuit, we will call it as wattless current. And one more small term also, power factor. In power factor is nothing. It is very easy. See, power was ERMS, IRMS cos phi. Class, this term that is present, cos phi. This is known as the power factor. And cos phi, we have been already using it. Remember, tan phi was XL by R. And remember, I had made you write cos phi was R divided by Z. So cos phi is simply your power factor. So whenever power factor is asked, write down cos phi. So it means here for purely resistive circuit, cos phi was equal to 1, right? Cos 0 was equal to 1. So it means power factor is 1 for purely resistive circuit. Or you can say power factor is 0 for purely inductive circuit. Like this also you can replace it. So just this term, cos phi, this is known as power factor. All right. So transformers we'll do, so in transformers we'll do, there you will see the current in the primary is almost wattless. So wattless current and power factors are also present. Inductor's energy and capacitor's energy is left. That we'll do. First, you note down these points. Any difficulty you have in here, let me know. Then one question comes, two questions we'll do. This derivation of this power, this is not so very important in the exams. This rarely comes to prove it. Usually questions come from it. But wattless current, since it was deleted, now it has been added. So there are a lot of chances that wattless current can be asked. We have multiplied and divided it by 2 because by this you cannot simplify it. So we require trigonometric identity, and trigonometric identity is only possible when we write 2 sine theta and sine B, means sine A into sine B. So just to make this trigonometric identity, we had to multiply it. See, this is proven trigonometrically in mathematics. You have a full long derivation how the second cosine term becomes zero. So no need to go into the details. Just remember, if cos theta is present, cos twice of theta is present, then when you take the average value of this, that becomes zero. So that's why we have it zero. Otherwise, the derivation for this, how this has become zero, that is a part of mathematics that you study in trigonometry. Yes, numericals will come, and maximum the chances of numericals are only based on this formula. We'll discuss the numericals as well. Definitely, numericals will come, and More than the derivation of this power, numerical is important. And small theoretical questions can be constructed from here. What is the power factor for purely resistive circuit? So you'll write unity 1. Or when is the formula for maximum power? Like this form, what's the average power for purely capacitive circuit? All these you can write it down. Definition of wattless current can be asked. Okay then. Now see, after this, no one question that comes, prove that average power is zero. We have studied that average power is zero by simply 90°. But if it comes to prove that average power associated with a capacitor or an inductor, mainly it comes with a capacitor is zero. It can also come for inductor. Steps are same. You can reuse any of it. Steps remain the same. It's just that one leads, which quantity leads differ. So that can be asked. See, energy for inductor is half Li square, and for capacitor, it's half Q square by C, or it's half CV square. So I've just written because we have already discussed this in the chapter number 2, where for capacitor and inductor, we have done it also. Both of it, we have discussed it. If it is asked to prove that average power is zero, see what we have to do. Let's take it for capacitor. If we take it for capacitor, see EMF will be equal to E naught sine omega t, while the current will be equal to I naught sine omega t plus pi by 2, because we all know current leads by 90 degree. Class, be prepared for your test as well. Next week you will be having a test on alternating current, because this chapter will almost be over by today. So next week and next class we will be completing with EM waves. EM waves is a very short lesson. So from the next week we can start with ray optics. So I is equal to I naught sine omega t. This can also be written as I naught. Scroll up. You have not done. You told me that you have completed it. This part you can copy it down. Later you can copy it down fast. I'll give you time. I is I naught sine omega t plus pi by 2, or you can even write it as I naught cos omega t. Both are valid. Both show that current leads by 90 degrees. And regarding the power, see, if I write work done is what? Work done is power into time. Power is work done by time. So work done will be what? Power multiplied by time. And power will be V into I dt. And we know EMF into I will be what? So dW will be E naught I naught sine omega t cos omega t dt. I'm not writing this entire term. It's better if I write as cos omega t. This is a shorter term to write. Now, if I want to find out the total work done, I just have to simply integrate both the terms. So work done will be what? See, class, before we integrate this, no, see, sine omega t cos omega t. This can directly be written as sine 2 omega t. We can directly write it by the identity. Sine 2 omega t by 2. Clear? So this is the work done. dW. And I have to integrate this only. Now when I'll integrate this, why am I integrating? Because average power will be what? Average power will be work done by time. All right. So here when we are integrating, we have to divide it by time to obtain the average power. Okay, so C class, from here E naught, I naught 2 and one capital T will also be there for power. For work done it won't be there, for power it will be there. So P average will be what? E naught, I naught by 2, and this T will be taken common. We'll be left with integration of sine 2 omega t dt. And obviously we are calculating it for a complete cycle. Dissipated per cycle we are calculating. So this will be. Now simple integration, this type of integration we have already discussed. E naught I naught by 2t is a constant. When you differentiate sine 2 omega t, we have done negative sign comes. Then you have cos 2 omega t and the constant term, that is 2 omega, it gets in the denominator. This we have discussed it a lot of times. So still you have any confusion, let me know, I'll again repeat it. Now putting on the limits. If you put in the limit, see, this becomes minus E naught I naught. Here, if we wish, we can write it in terms of omega, we can elaborate. 2 pi by t we can write. Let this be 2t only. Let's write the values. So see, this part becomes, this is cos 2 omega by omega t. Omega can be taken out, or both these 2 omega can be taken out. This 2 omega which is present, you can bring it out here. So this becomes 4t omega. Now you just have minus 2 omega t there. Not even minus, only cos 2 omega t. Minus also I have taken out. So cos, this becomes cos 2 omega capital T minus cos 0 degree. Upper limit minus lower limit. So minus E naught I naught by 4t omega. This becomes cos 2 into 2 pi by capital T. This is 2 pi by t for omega. See, this is omega into t minus 1. Cos 4 pi is 1. You obtain E naught I naught by 4t omega as 1 minus 1, which is 0. So this is one proof question that comes. Okay, and this can be asked in the exam. A lot of chances are there that this wattless current power factor can be asked from this topic. Okay, one numerical we have, an easy numerical. This is not a tough numerical. Let's discuss this and so that you can note all these parts together. See, a light bulb is rated at 100 watt for a 220 volt supply. So power is given to you, ERMS is given to you. You have to tell the peak voltage, resistance, RMS value. See, this is not difficult. Why? Because you have ERMS given as 220 volt, and one more thing that you have is power. Power is given as 100 watt. The first part is asking peak value of voltage, means E naught has been asked. So how will you get E naught? As Sahal only answered in today's class, that ERMS can be written as E naught by root 2. So from here, E naught can be written as ERMS multiplied by root 2. So ERMS will be, E naught will be 220 root 2 volts. Fine. You can even put the value of root 2 as 1.41, so you will obtain a specific value. For second part asked you the resistance. See, resistance formula will be similar to what you have studied in case of in the previous cases. Resistance will be simply square of Vrms by P. We write power as V square by R. So R will be written as V square by P. So that becomes 220 whole square by P. Power is 100. So that will be 22's whole square, no? Because both the zeros get cancelled. So it will become 484. It should be 484 ohms because 22 square is there. And third part is asking IRMS. See, IRMS, P is equal to VI. So I will be equal to power by V. Power is 100, V is 220. This much of amperes will be the answer. So I think this should be around 0.45 amperes. Just cross check it once, your calculations. So 2 questions we have done. This was a very easy question, very easy question based on upon the previous formulas only. It's just that power, how power can be used, we have seen. More important is this, prove that average power is 0. All right, class. Note it down. Note these also, inductors energy, capacitors energy. And if you have any queries in between, please clarify. Fahad has a very good habit. He keeps on texting whatever doubt he gets in the part right then and there only. So by that, the doubt gets clarified on that moment only. So others also can keep on texting as well, or you can even unmute yourself, both the ways. Second last line means this one. See, for this line, minus E naught I naught, cos 2 omega t. Omega can be written as 2 pi by t, this t, this 2, this cos. So this tt gets cancelled. We are left with cos 4 pi. Understood? Now, and cos 4 pi, this is 1. ERMS has 220 volts, that is given in the question. Is rated at 100 watt and 220 volt supply. So I've told you already that whenever you have such a supply, nothing is mentioned, that is your RMS value. Done till here, class? LC oscillations are not part of your syllabus. No need to do LC oscillations. Done? Or anybody is writing? So did you understand till here? Power, energy, because one last topic is left, that is transformers. So before we start with transformers, any doubts still here? All of you? Ammon, Rufia, Reem, clear? Rifat, understood? Wafia? Okay. So if anybody has any doubts, you can ask me. Transformers, let's do. Transformers is not difficult. Transformers are the easiest part of your this lesson. Alternating current. See, transformers, just understand, transformer is an electrical device. It does what? It either converts a low voltage into a high voltage or a high voltage into a low voltage. That is just the function of transformer. This is the function of transformer. Low voltage is there, high voltage is there. So either it can convert low voltage to high voltage. If it converts low to high, it means it is pushing it up. Voltage has been pushed up. So if it's from low to high, it is known as step up transformer. And if the higher voltage is brought down towards the lower one, so if it decreases the input voltage, then we say it is a step down transformer. That is what is written, and that is what is meant by transformer. Transformers are of two types, step up, step down. If voltage increases, step up. If voltage decreases, step down. Clear? Easy. See, transformers is easy. Whatever tough part was there, we have completed in AC. Transformers is an easy part. Even the formulas are also very easy for it. See, it says what? It is an electrical device. Yes. A transformer, it is an electrical device for converting an alternating current at low voltage to high voltage, or the current is converted from high voltage to low voltage. If it converts from low to high, means it increases the input voltage, we say it is the type of transformers are known as step-up transformers, and which decrease the input voltage. It decreases the input voltage from high to low, from high voltage to low voltage. These are known as step down transformers. Clear? Easy. I hope you'll remember. Principle, again, principle you have already covered. No need to do it again. Principle is totally the complete principle of mutual induction. Two coils are there. I think when we were doing induction that time, also I had stated that we'll repeat it in terms in case of alternating current also. So same thing. Now construction, regarding the construction of it. Two types of constructions are there. You have two wires. Primary wires are there, secondary wires are there. Wires basically coils. Mutual induction is there, no? So mutual induction mein kya hai? In case of mutual induction, you have a primary coil, you have a secondary coil. In the primary coil, flux changes, magnetic field increases, decreases, flux changes. And so there is production of induced EMF in the other neighboring coil. That's what we have studied for mutual induction. Now, based upon the arrangement of the primary and secondary coil, we have two types of transformers. I'll show you. See, if the transformers are, if the primary and secondary wire are held on the edges and they are separated, the primary and secondary wires do not touch each other, we say it is a core type transformer. Fine. This is known as a core type transformer. And the second type of transformer, this is known as a core type transformer, like this. This is core type. And if they are joined, Joined. The primary and secondary wires are overlapped. These are joined. Then we say this is known as the shell type transformer. So they are, the primary and secondary coils are separated in case of core type. Still induction can be done because we have studied there's no need of contact for both the coils for mutual induction to occur. And for shell type as well, for shell type we have primary and secondary in direct contact with each other. So transformer, types of transformer, and classification of or the construction of transformers. This is what is meant by construction of transformers. Now, the working of transformer, we have, this is just simple mutual induction. That's why this part will be covered fastly. You will be able to understand. See, this is just whatever you know about mutual induction, write it for the working as well. As the alternating current flows through the primary coil, it generates alternating magnetic flux. We have studied in case of EMI magnetic flux changes. This alternating current passes through the secondary coil. So if magnetic flux has been changed in the primary coil, then induced EMF will occur in the secondary coil. Fine? Simple, whatever you have studied for mutual induction. So as the alternating current flows through the primary, it generates alternating magnetic flux, which passes through the secondary coil. Due to change in the magnetic flux, induced EMF will occur in the secondary. Self-induced EMF will be there in the primary coil as well. Means self-induction can occur within the primary, but since both the coils are present, primary and secondary, mutual induction will occur. That's the principle of it. Formula of this is also easy and simple to write. E is equal to minus d phi over dt. So if n number of turns are there, so you will multiply it by n. E is equal to minus n d phi over dt. So for primary coil, I am writing it as EP is equal to minus np d phi over dt, where EP is what? Voltage in the primary coil, np is number of turns in the primary. If you write the same thing for secondary, you just add S over here, voltage in secondary and number of turns of secondary. So ES is equal to minus NS d phi over dt. When you'll take the ratio of both of these, see what you'll get. Here, this is the formula part from where the very easy questions come. Calculations are also very easy. So EP by ES means voltage in the primary by voltage in the secondary is equal to number of turns in the primary by number of turns in the secondary coil. How I have done this? I have done this with the help of that only. E is equal to minus NP d phi over dt and E is equal to minus ES is equal to minus NS d phi over dt. D phi over dt, d phi over dt and minus gets cancelled. You get this formula only, right? This formula is just given by the ratio of both these quantities. See class, for voltage and number of turns, now remember, if EP is in the numerator, NP will come in the numerator. If ES is in the denominator, NS will be in the denominator. If you write ES in the numerator and EP in the denominator, so write NS in the numerator and NP in the denominator. Secondary will come in front of secondary, primary will come in front of primary for these coils, for a voltage and number of turns. But if it is for current, see P is equal to VI already. From here, voltage will be inversely proportional to current. So EP by ES can be written as NP by NS. But when you write current, it's secondary on the numerator and primary in the denominator. Whatever you have written for these voltages and number of turns, reverse it for current because current is inversely proportional according to this formula. EP by ES is NP by NS, but it won't be equal to IP by IS. Your answer will completely become wrong and you will get a huge amount of current. So it's IS by IP because it's inversely proportional. Number of turns or voltage ko saath mein rakhna hai. Means both of them, voltages and number of turns will be kept together. Kept together in the sense if it's primary together, primary, if it's secondary, secondary. Reverse current for it. If you have written it S by EP, right, and S by NP, But do not write IS by IP. That time write IP by IS. Like this in one single line, this is all the formula for transformer. All right, power for also transformer you can write. Power input will be, this is just the theory part, then you can note it down. Power input will be what? EPIP. Power output will be ESIS. Why? Power is equal to VI. So if it's for input, means for the primary, just write it P. Current in the primary coil multiplied by voltage in the primary coil. If you're writing output, simply it will be VSIS, means voltage in the secondary by current in the secondary. So efficiency, you must have heard in your class 11th if you have done. I don't know whether it was included in your school's syllabus or not last year. Have you all done the efficiency of, when in thermodynamics, efficiency and coefficient of performance for refrigerator, efficiency of Carnot engine? I think it was deleted last year. Have you all done this, efficiency of Carnot engine and refrigerators? Done or not? Yes or no? Coefficient of performance of refrigerators and all. No, you have not done, Fahad. Only Fahad remembers. Others? You have not done. I think it was deleted last year in 11th. But some schools do, because in 11th standard we have the liberty. That's why. Anyways, efficiency means how much efficient is a transformer. If you give some amount of power, how much outcome of the power will the transformer provide you? So that is efficiency is power output by power input into 100. If I talk about an ideal transformer, a transformer which is ideal, so efficiency will be 100%. It will be 100% efficient. Means whatever power input you are providing, exactly output power you will get. No loss of heat energy, no. But in reality, we have some efficiencies less. Like 90% it can be efficient, 75% transformer can be efficient. Because in nature, we have heat losses and other factors. So efficiency cannot be 100%. But if you talk about ideal situation, ideal transformer, efficiency has to be 100%. Where the transformer works very well. Is this clear? Transformer, very small topic and an easy topic from this whole chapter, alternating current. Did you understand or not? Yes, class? Are you all listening? Or should I call the names? Okay, Rafat, Emin, Wafi. Okay. Fahad. So if it's clear, then good, just note it down. Okay, then I think all of you have understood this stream. So this is easy. Transformers questions are directly based on this formula. I'll show you one question also. Let me show you a question if I have. I have this question. Question is lengthy, but the question is actually very small. It is looking lengthy. You note this down. You note the above portion. We can do the numerical in the next class as well. This is a huge part that you have to copy it down. No? So you can copy it down. Wherever you have doubts, ask me. And from transformers, direct numericals come. And that formula will be sufficient, which we have encircled. If you will complete till here, efficiency of a transformer, you can leave the meeting. Already your time is up. One numerical is there, as I've told you, easy numerical based on this formula that you can take the screenshot and try at home. Otherwise, we'll discuss it on Thursday. And also, you'll be having a test of AC next week, that is 18th. So all those who are done, you all can leave. Okay, thank you so much.
Thank you, ma'am. Allah Hafiz.
Okay, Allah Hafiz.
Ma'am,
Yes, Fahad, say.
ma'am, I had doubt in like numericals, like how we will get to know whether it is IRMS or ERMS.
See, IRMS, ERMS, the current that the voltage that you have, which is present in the circuit, and nothing is mentioned. Like you have, let's say, 220 volt is there connected with a frequency of 50 hertz, like this, if you have. So, for such cases, it is given that the current or the voltage that is present by default, that is RMS value. If it is peak value, if it is average value, or any other value, then we take the that will be specifically mentioned to you. But by default, when nothing is mentioned, we take the RMS value, because the way we have normal voltage and the way we have normal current for DC circuits, for AC circuits, normal current and normal voltages are ERMS and IRMS, root mean square, because that gives you the mean value of all the current and the values of voltages that will be obtained when the AC dynamo will rotate. For that rotation only, out of all the values you have, one of the values will be the highest, one of the values that will be the peak value. One value will be the maximum, because so many values are there. The way in a class, so many students are there, one student scores the highest score. But if you take the average of all the score, so this average score that we get for a class, that is similar to what is ERMS and IRMS. And that maximum or highest score obtained by a student, that is the peak value for E and peak value for I. So if nothing is mentioned to you in the numerical, or it is given along with the AC dynamo like this, then it definitely means this is ERMS value. If it is E naught or I naught, that will be specified to you. Clear, Fahad?
Yes, ma'am. So, like here it is 220 volts. So we can take it as ERMS. If there was
Yes.
one A, like ampere, then it would be IRMS, right?
IRMS, yes, that would have been IRMS. Like in this question, this has straight away said for a 220 volt supply. Now it is referring to AC, and 220 volt supply in case of AC will be what? This is the supply, and which device supplies AC, which controls it? AC dynamo. That's what we have studied, no? When the coil rotates and angle changes. So that's why this becomes ERMs. Let's say some current is given to you. Let's say this was 0.45. Instead of 220 volt, the question would have given you a light bulb is there at this power, and the current is 0.45. So nothing is given, that is IRMS value. If a peak value is given, that will be mentioned. Or one more hint you can take from the question. By chance, if the question asks you calculate the, for example, here the question would have asked you calculate the ERMS value, then you, in that case, you would have considered this